But the issue is, of course, so we've got our density of points in K space, but we don't want K space, we want energy space. So now we need to convert from K space into energy space. And I'm going to show you the result and vaguely how we get there. So we start off by writing down that the energy is h bar squared k squared over 2m, and I'm going to derive this in case it's not intuitive to you. And then we find out that our density of points of energy space, G of E, is this thing here. It goes as e to the half. Okay, so let's have a go at this. Okay, so let's start off by deriving our expression for the energy. So we start using the expression for the de Broglie wavelength. So de Broglie wavelength, P is equal to h over lambda. And if we convert lambda into k, we get hk over 2 pi, which is, of course, simply h bar k. And that might look familiar to you from quantum mechanics. So now we write our energy as p squared over 2m. And I hope you can convince yourself this is equivalent to a half mv squared, but because we tend to not use velocities when we're dealing with quantum mechanical things, because momentum is a more useful variable. So we're going to work in terms of momentum, not in terms of velocity. So we write our energy not as a half mv squared like we would do for normal kinetic energy, we write it as p squared over 2m. Okay, so if E is p squared over 2m and p is h bar k, we get E is h bar squared k squared over 2m, and we can rearrange that to write it in terms of k. So k squared is 2me over h bar squared. Okay, now let's look at our density of states in k space. So we had our f of k dk is 4k squared over 2 pi squared dk. Now, to convert this into a density of energy states, what we need to do is we need to eliminate all of these k's. So the first one is quite easy because we know what k squared is, we've got it here, but we also need an expression for dk here. And we need to get that by differentiating this thing up here. Okay, so that's what we're going to try and do now. We're going to try and convert from dk to dE. So E is h bar squared k squared over 2m. And so we have dE is equal to h bar squared over 2m times 2k dk, which is h bar squared over m k dk. Fine. Now we need to substitute for this k here to get rid of it. D. So k is the square root of 2me over h bar squared. So I can now substitute this in. And we have from previously, we have our expression for decay. So decay is m over k h bar squared dE. And we know we've just arrived what k is here. So we can say dk is m over h bar squared. So 1 over k. So I've got an h bar on the top. I've square rooted that over the square root of 2me dE. So now we're ready to put everything into our expression for f of k dk, and thereby transform it into an f of e dE, a density of energy states. So we have f of k dk equals b k squared over 2 pi squared dk. Now, this becomes, okay, so f of e dE equals, let's have this v over 2 pi squared. And then we want our k squared, which is 2me over h bar squared. And now times our expression for decay. So we've got m over h bar square root 2me dE. Okay, so now we can get rid of those 2's. We can turn that into an h bar cubed. So we've got v over pi squared. We've got an h bar cubed on the bottom. We've got an m and an e. Got another m there, so that becomes n squared times 1 over the square root of 2me dE. Now we can see that we've got, so we've got to do something with these roots here. We've got problems with our roots. So let's write this out a bit more neatly. Pi squared h bar cubed. So we've got an e over a root e. So that's going to give us root e on the top. Times by, we've got an m squared here, and we've got a square root of 2m there. We've dealt with that e dE. Okay, now we've got m squared over the square root of m. So that is m to the 3 over 2. But I'm going to take this 2 with us. So that gives us 2m to the 3 over 2. So our m's are right, but we've taken our 2 inside this 3 over 2. So we need to divide it by something that gives us the same as this root 2 on the bottom. And of course, what we need to divide it by is 4. And then we've got our dE on the end. So this gives us the grand result that f of e dE is equal to v over 4 pi squared h bar cubed 2m to the 3 over 2 e to the half dE. And this is our density of energy states. And if you're not convinced that 2 to the 3 over 2 divided by 4, so 2 to the 3 over 2 divided by 4 is equal to root 2, try it on your calculator, because that's what I did to check.